Hello again. I will be speaking about the more advanced models than on the previous talk. So we will tackle a bit the recurrent neural networks. So first of all, I would like to actually describe what's the one of the very classical NLP tasks, which is called language modeling. In more details, what does it mean? I will be speaking about recurrent neural networks and some incarnation of it, like long short-term memory units. Then I'm gonna describe the task of machine translation, how it can be addressed, and I will speak about some more exotic tasks. Language modeling is actually one of the very old NLP tasks, and I'm not sure, actually it doesn't fit into screen, I think. Yeah, it's better now. So it's one of the oldest NLP tasks, and the purpose of it is to essentially assign the probabilities to sentences. So sentences consist of words, and those words are not completely randomly glued together. There is some specific order, some combinations occur more often than others, and as I mentioned, for instance, after word Obama, it's unlikely the word Delphine is unlikely to occur. Language modeling is actually used in many places, so it's used in machine translation, speech recognition, and so on. Also I want to say that the baseline given by n-gram, I will describe what is exactly the n-gram model. It's actually quite challenging to beat. So it's a very simple model, and it's not that easy actually to beat it. So, the natural language, the sentences are the sequences, and we would like to assign a probability to every single sequence. So we would like to assign a probability to every single sequence of words, such that if you sum over all possible in the word sequences, then it will sum up to 1. This way, for instance, the sentence, how are you? That's the sentence that is actually likely to happen. You would like to assign quite high probability, and to sentence like, how banana you, it doesn't make sense at all, so you would like to assign quite low probability. So you can say that from probabilistic perspective, you would like to learn the probabilities of sequences, so x1, x2, and so on, those correspond to words. This probability will be parameterized. We can parameterize it in various ways. So, for instance, one of the parameterization is using n-grams, one of the parameterization is using n-grams. One of the parameterization is using recurrent neural network. And what I wrote down over here is actually a generic property of the probability, of conditional probability, that that you can decompose the probability of a sequence x1, x2 up to xn as the multiplication of conditional probabilities. So in order to say what's the probability of a sequence, it's enough to know what's the probability of the first word, then what's the probability of a second word given the first word, then what's the probability of third word given the first and second word, and so on. So that's the very generic equality which holds for any probability distribution. It's a multiplication of the probabilities of xi given the past xi's. Okay? So n-grams, as I mentioned, that's the language model that actually has some independence assumptions. So particularly biagram assumes that as over here we decompose the probability x1, x2 up to xn as the multiplication of xi with all previous things that occurred in this given sequence. In case of a bigram or n-gram, we actually throw away many of the words before, and we just say, let's assume for the simplicity, in order to make a simple tractable model, let's assume that actually current word just depends on the previous word, not on the, let's say, 5 previous words or 6, or let's say entire context and situation. It depends just on the previous word. Okay, so then you are saying, I will decompose the probability of a sequence x1, x2 up to xn as the multiplication of conditional probabilities of xi given the previous word xi minus 1. Or for instance, if you want to have a triagram which relies on the 2 previous words, you are saying, oh, I will decompose it as the probability of a given word, conditioned on 2 previous words, and so on. Okay? So, to give you some example, there is a sentence, this is a sentence. If we would like to decompose it using triagram, you would say, probability of this sentence is such as the probability of word this multiplied with a probability of is given this, then probability of A given this is, and the probability of sentence is A. So you can notice that toward the end we actually condition on fewer words. We are not conditioning on all the previous words, but up to 2. So here is A given this is, so that's still all, but then in case of sentence, it's just conditioned on is A. So the way how n-gram model actually estimates these values, the probabilities that we have in this equation, is using counts. So we can take a bunch of data and count how often it happens that, for instance, we have a word sentence and 2 previous words are is and A. So you can count how often it happened, and this gives you actually maximum likelihood estimator for this probability distribution. So it's a very simple model because it's essentially a lookup table. You count how many times the things occur. There is several issues with this model. So let's say if your vocabulary size is 1 million, then if you want to store all possible diagrams, then it would be of a huge size, million over million. But maybe you don't need to store all of them because many of words doesn't occur that often. But let's say the bigger n is in n-gram, then actually the fewer examples you're gonna have. So you are storing, you have to store, it's kind of a tensor, n-dimensional tensor. So let's say if you have a triagram, it's the million by million by million combinations in the sense. Of course, you don't have to store all of them, but you will have fewer and fewer entries. So let's say the more memory you want to have about the past, the fewer entries you will have in your matrix. Theoretically, yeah. As I mentioned, the fundamental problem behind the n-gram is that this simplistic model actually grows exponentially in number of parameters as you increase n. So you can say, oh, if we want to have really smart systems, they should have some memory about what happened many words ago. But the more memory we give, the parameters actually keep on growing exponentially. So it's not something that can scale up. But I just want to, I want to say that I have to be careful. Let's say n-gram is essentially a quite powerful still language model. So in many applications it's good enough. But the neural networks, to some extent, they try to compress which words they co-occur with each other, or let's say what are the longer, longer dependencies. So language models currently are actually the state of the art in terms of, let's say, machine translation and automatic speech recognition and so on. And there are few, let's say, fundamental architectures that people use. So one is the feed-forward that I described earlier today. Essentially consumes the input of the fixed size, does several matrix multiplication, and outputs the output. There is something called recurrent, and I will speak about it, and I guess that the speakers who will be speaking more about the vision, they will describe the convolutional neural network. Benjio, over 10 years ago, he proposed to train a language model, a model that assigns the probability to sentences just by using neural network. So as I just feed-forward neural network. So as I mentioned, the problem with n-grams is as the, let's say, history, as if we want to increase the length of dependency into the past, then we are actually getting hit by the exponential growth of the parameters. And the hope is maybe if we'll have a neural network, somehow because of parameter sharing and so on, we will avoid this problem. So Benjio proposed, let's take several words from the past, let's have a few layers, and let's try to predict the next word. So that's the very simplistic, that's the very simple language model, but still it has a fixed length of memory. So it cannot, let's say, arbitrarily refer to words that occurred many words ago. So you can imagine that in some, if you really want to have a proper understanding of a speech, you cannot just like that purge words that happened some time ago. You cannot just like that, let's say, don't care about the order. In order to get the proper understanding of text, you will need to actually have to remember what happened many steps ago. So here, that's one of the representations that to some extent deals with consuming several words from the past in order to predict the next one. But the question is there any smarter way to consume arbitrary number of words from the past in order to predict the next word? And the answer is yes. So idea behind is that essentially we are reusing the same representation, the same weights as we consume words from the past. So let me give you some schema. So it means the following. Let's say here is the sentence, my name is Wojciech, okay? And we consume, let's say, word my. Then we get some hidden representation. We try to predict name, but in the same time, we are actually producing a hidden state that it's used for the next word prediction. So that means that as we produced here a hidden state, then this hidden state is consumed during the next time step with the same neural network that uses the same weights. That's the reason behind this use. The name recurrent is because it uses the same weights. So you can imagine that, let me back off a little bit. You can imagine that to some extent you would like to use the same weights to consume the words at different time. So it's the same way, there is no, I'm not changing my brain every second like I completely all the weights as I'm consuming every consecutive word. I'm using the same brain, and over the time it passes the state. So the same way over here we want to consume word, produce a hidden representation, and this hidden representation hopefully will be encoding whatever happened up to now. And the same way, let's say we are passing this hidden representation to next time step, we are consuming a next word, and we are producing hidden representation which is passed further. So that's the essentially recurrent neural network. So after consumption of mine, we are predicting name. After consumption of name, we are predicting is. After consumption of is, we are predicting Wojciech. You can imagine that it's the same as the output. The targets are the same as the input, but shifted by one. Okay. And the way of training a neural language model is using classical SGD with backpropagation, but there is like there is one important thing to note. Okay, there is one important thing to note. As we share the same weights, we have to be careful how to optimize it, and algorithm behind, I will describe the algorithm, is called backpropagation through time. It's a very simple algorithm. So the intuition behind the backpropagation through time is that we unroll a recurrent neural network, so it becomes somehow feed-forward neural network. So even though we have the same weights over here and over here and over here, or over here and over here and over here, those are like a corresponding weights, we can perceive it as just a feed-forward neural network. So we unroll it over the time. And then this is essentially a feed-forward network with shared weights. And then we backpropagate the same way as we would do it in a feed-forward network. Somehow it's the backpropagation is somehow it's a dual thing to the forward propagation. So it's that the flow of gradients is in the opposite direction as the flow of data when it's consumed. So you can imagine that, let's say we are consuming the computation goes from left to right, and here it goes as the arrows show. So here it goes from left to right, and here it goes as the arrows show. And then during backpropagation, things are going in completely opposite order. So you are getting signal from here, it goes back, and then through the green arrow, it goes to the previous time step, and so on. So one of the choices is the question. So as we are unrolling the recurrent neural network, you can imagine that as the text, we think about the text as the infinite sequence. Okay, you have infinite sequence of words. Okay, and you want to predict the next word, but then you would have to unroll your recurrent neural network for infinite number of steps, and obviously that's not feasible. So usually you unroll it for some fixed number of time steps, and then you backpropagate with respect to it. Like 5, 10, 20, 50 or so. And there is few actually problems that occur when you do backpropagation through time. So two common problems that are that you will notice is something called vanishing and exploding gradient. So you can imagine that some sort of approximation to what is going on in case of recurrent network is that it iterates multiplication through matrix, okay? And as you keep on multiplying the same thing with matrix, or kind of the same thing, because let's say there is different input coming from the bottom, but the state somewhat, it's multiple times multiplied with the same matrix, then what can happen is as, let's say, if there is any eigenvalue of the matrix bigger than 1, then as you will keep on multiplying with the same matrix, you will get the explosion of the value. And if there is some eigenvalue which is sort of smaller than 1, then after multiplication multiple times, all the information will actually get down to 0, and you won't get any signal. So those are the problems that people really experience while training neural networks. And there are some, maybe not well mathematically grounded, the methods to actually alleviate it. You can think that, say, you would like to really unroll for many time steps, because the more time steps you unroll, then you might capture the longer distance dependencies. But also, it's problematic in the sense that then you are having these problems like a vanishing or exploding gradient. And one of actually proposals for the vanishing gradient is something called LSTM. So I would say it stands for long short-term memory unit. I mean, it's actually these days it's quite popular. I would say I'm using it by myself. It's kind of ad hoc solution. So let's say I would wish to see a solution which is actually somewhat derived in mathematical way or so. But it's kind of ad hoc, and there were many actually incarnations of it, and people also came out with some different units that somewhat help the vanishing gradient problem. And the way how actually LSTM works is, or let's say what's the motivation behind. The motivation behind is that in order to keep a memory for a long time, maybe it would be cool to store it somehow inside and then be able to decide when we want to retrieve it or just remove it. So you can imagine that the same way as you have a RAM memory in computer, which is not differentiable in the sense you can store their information and then retrieve it. This is incarnation of something like that, but differentiable. Or let's say that was the motivation behind. If we want to avoid the information being removed over the time, maybe we should be able to store it somewhere and then be able to decide when we want to retrieve it. So LSTM is designed in the way that it has internally some gates that they modulate and they allow to, let's say, decide the network either to retrieve or replace the value which is stored within so-called cell. So there is a cell inside, and then there is something called input gate, output gate, forget gate. I would say many of these things are somewhat arbitrary, so I wouldn't pay that much attention to it. But I want to emphasize that actually it's a model that works it's quite stable. Over the time, they tweak the parameters so well, or they got such a proper activation functions here and there, that it is able to solve the problems from variety of domains. Also, I want to emphasize that actually there is many variations of it. So people, they were cutting and adding connections here and there. Sometimes it helps, sometimes it doesn't, and it's unclear. Another problem that I mentioned is so-called exploding gradient. So if we iterate multiple times, the kind of, in case of matrix multiplication, you can, it might happen that the values will be magnified exponentially. So it turns out that the solution that people use, which is also not mathematically grounded but seems to work, is so-called gradient clipping. So you look at the magnitude of the gradient, and if it's above some threshold, then you scale it down. And from an empirical perspective, it happens that, or let's say that's what I'm doing, or that's what people do when they train recurrent neural networks. Usually, it works in the way that you want to clip, that the gradient is mainly clipped toward the beginning. So you can think that there may be random initialization cause some instabilities and so on, but over the time, as you are training it, actually very infrequently you are hitting the threshold when the magnitude is actually above the one coming from the clipping. So you can think that obviously when we introduce gradient clipping, it's not anymore the optimization based on the gradient descent or the stochastic gradient descent, because it's the gradient with modified magnitude. But in reality, such regime occurs only at the very beginning of training, and over the time, actually, network doesn't hit the threshold that often. And also, threshold should be chosen in such a way that usually over the training, it's not hit later on. So here, let me give you some comparison in terms of the methods on the small data set. So as I mentioned, okay, you should choose the methods depending on your task and what you want to achieve and so on. So obviously, if you have access to infinite amount of data and so on, you should first of all try with the cheapest possible models. Or maybe if your method might not care that much, or if your task might be not that important, the order of words and so on, then you should choose the easier method. And here is an example on the small data set. So on the small data sets works in the way that maybe if you will have a better model, then you can achieve the better performance in the sense. So a data set has just 1 million words. It's called entry bank or PTD. And the measure over here is so-called perplexity. So it works in the way that perplexity is exponent of the entropy, or or the average entropy. So what does it mean? To give you some intuition or how we measure it. So we have a training data on which we train the language model, which should learn what's the probability of sentences. Okay, so it should give it should, let's say, kind of know what is the new upcoming word. You can also imagine, or there are even some evidences that we also have, we learned something called the language model, in the sense that you, in order to understand me, you are not assuming that I'm going to say any particular random word, but you have some probability distribution over what are the next upcoming words, and that actually simplifies, or this helps you to decode what I'm saying. So, because you have some prior knowledge about what are the possible things to say. So in terms of training, or let's say in terms of the metric, it works in the way that you train on training set to maximize the probability of sentences, and then you take a test set and you measure what's the average probability of what's the average probability of words given by the model. So let's say I'm asking model, what's the probability of the next word? And then I'm telling, oh, the next word was this word. And I'm asking, what's the probability for next word? He's telling me, that there is a sentence, I don't know, how are you? What's the probability for how? That's the test sentence. It's telling me some probability. Then I'm giving the word how. I'm asking what's the probability for art. Then I'm giving the word art, and I'm asking for the probability for the next sentence. Then I'm essentially computing average over it. So it tells me somehow how model was certain about what's the real next word, okay? So how it was likely to guess. And that's the data which this model never seen. So means if it would have no knowledge whatsoever, it should assign equal probability to every word. But if it would know somehow what's the probability, then it might assign much higher probability to things that are likely to happen and much lower to unlikely words. So perplexity, essentially, it's the exponent, I think, of the exponent of, I don't want to screw it up, I think it's the exponent of the average log likelihood or something like that. And the reason why people take an exponent instead of the average itself is because then the numbers kind of look bigger and they are more comparable. So let's say if you if you just have a logarithm of it, then you could say, oh, I made an improvement of 0.02. But in this case, those are the nice improvements. So perplexity is the common metric of measuring performance on the language modeling task. And as I mentioned, the n-gram gives you also a way to measure the probability for the next word. One of the important things actually about the language modeling is that to some extent you have to allow for positive probability for every single thing. If your model would assign probability 0 to something that really occurred, then actually perplexity, because I think it's the average of logarithms, it would be infinity. So then you are screwed up. In the sense that perplexity, also some people perceive it as the measure of smoothness. So you have somehow to assign probabilities, you have to distribute the probabilities over the words in such a way that even in the worst case scenario, you won't be hit by performance. Because if you would assign the too low probability to some words that really occurred, then your loss, then you will incur infinite loss. And you can see over here in terms of like a comparison between models that n-gram is achieving something about 140, maybe some models based on the feed-forward network, they are similarly getting 140. Classical recurrent net is getting 120, so there is some improvement, like by 10%. And actually, at LSTM, it's possible to get twice as little perplexity. The lower, the better. You can imagine if perplexity would be equal to 1, then it means that model knows exactly what's the next word. It's certain about the next word. Everything is deterministic. So it's also another way of thinking about perplexity is that it's a branching factor about what are the next possible outcomes. Okay, so I will speak a little bit now about the, let's say, quite important application, which is the machine translation. And that's the work by a friend of mine, Ilya. And I will describe how recurrent neural networks, or LSTM in particular, can be used to actually, let's say, address machine translation problems. So it's done in the way that actually, in case of language model, we're saying, oh, at every time step we should produce some output. We're saying, oh, it should be the next word or so. But let's say recurrent networks, they allow to actually learn arbitrary mapping from a sequence to sequence. So you can imagine that you have a sentence in one language, A, B, C, D. While consuming it, you are not actually emitting any symbols. You are saying, oh, I don't care about what the network produces. And then at the very end, after you read the dot, you start actually producing a target sequence, X, Y, Z, Q. And similarly, as in language modeling, it might be actually beneficial for a network to provide what was the, let's say, correct answer or so. So let's say the target sequence, similarly as in language model, is shifted by 1. But in case of the input sequence, you are not predicting anything. So it's one of the sentences, let's say, in English, another one is in Polish or so. Okay, so you try to train a neural network to learn such a complicated mapping from sequences of text in English to sequences of text of words in Polish. You can also, let's say, from probabilistic perspective, you are essentially learning a conditional model. So it's or conditional distribution is the conditional distribution of emitting targets sentences given the input sentences. And once again, we are maximizing log probability, so that's very common metric to maximize. So it's important to, okay, so in the similar, there is few caveats. First of all, after reading the input sentence, one of the problems is that we have somehow, or the model has to somehow encode entire input within the fixed size representation. So let's say you have 1,000 dimensions between the between, let's say, green and purple part of the network. And in order to solve the problem of translation, the network has to encode here entire meaning of the sentence in order to be able to produce something. There is no more access to the input sentence. And one more thing to say is that actually, in the similar time, there was work on the same application coming both from Google, so that's the work by Ilya who's covered, and from University of Montreal. People, they use slightly different techniques. Maybe I will mention it later on, but they are based on the very similar approach. Okay. So as I mentioned, the entire representation after consumption is stored in the single state of LSTM, of recurrent neural network. And one more thing that we have to solve during testing is so-called decoding. So you can imagine that even though we are getting a probability distribution, so let's say after consuming input sentence, we are getting probability distribution over the output sentences. So let's say if we consume a sentence in English, we are getting probability distribution over sentences in Polish, but we want really to find the sentence which has the highest possible probability. So the sentence which has the highest possible probability, that's the sentence which is the LSTM gives us the conditional probabilities for the subsequent words. So it's the conditional probability of a word given the previous words. And we would like to find the sentence which gives the highest multiplication of this probability. So that's the probability of entire sentence. You might think that, oh, let's just choose at every location most likely word, and that's something reasonable to do. But the problem is that maybe if you have chosen the most likely first word, then actually all other words will be of the smaller probability. Maybe it was the better off to choose second most likely word, and then you have very likely sentence. Okay? So this is so-called decoding. In reality, if you would like to really be able to find a sentence with the highest probability, you'd have to enumerate all possible sentences, and then, which is exponentially many, evaluate them all, and then pick one which is the most likely. But maybe it's unnecessary, and we can use a greedy strategy. So the greedy strategy, in the nutshell, this is called so-called beam search. So one strategy that I mentioned, which is very sensible, is to use the just to pick most likely word, and so on. And this way, it will give you one possible output sentence. But another approach is to keep simultaneously and partial translations. It's called beam of the size n, and then try to look what are the, for each of them, what are the next possible words, and then keep on and attach to the previous translations, and then then limit it back to the and partial translations. So I would say in the classical machine translation, usually people, they had to do beam searches of the massive sizes, like thousands of possible sentences. So let's say if you have language model actually based on n-gram, it turns out that that's what was happening in the production translation systems, that you had to evaluate thousands of sentences simultaneously. But the nice part about the n-gram language model is that it's very cheap to evaluate, because it's a lookup table. So you just look into memory, what's the probability of some combination of words, and you can very cheaply evaluate it. In case of neural networks, especially when we have massive models, it might be order of magnitude more expensive. But it turns out that from application perspective, very tiny beam searches, they already give you majority of performance. So let's say that also the cost, if you have a beam search of size n, then the cost actually becomes cost of evaluation becomes n times higher. So let's say having just the beam search of size 2 costs you twice as much as just evaluating network at the argmaxes of the possible answers. I want also to emphasize that from production perspective, especially in the large companies, it's actually much more important what's the test time rather than the training time. So you might think, oh, it takes so long, it's 1 week of training to train something. But in reality, later on when you are going to serve it to millions of people, the real cost for you is actually to deploy it on thousands of machines and keep on evaluating it. So you really want to make sure that actually you are not paying much on this stage, rather than the training time, which you really don't care. If you will give hundreds of machines to researchers, it doesn't matter in the sense. Metric that is used actually for machine translation is so-called blue score. And blue score works in the way that it's as you have a target sentence, so you can think, oh, why we don't use the perplexity for the metric in translation? The problem is that there are many machine translation models that actually can generate for you translation, but they are not probabilistic models. So they don't assign the probability to sentences, and they won't give you conditional probability, because that would be one way of evaluating models. Let's get the real, let's get the correct answers, and let's measure what is the probability of them. If the probability of correct answers is high, then our model is great. But the blue score works in the way that your model has to emit sentences, and then you essentially measure the number of common unigrams, bigrams, trigrams, and so on with a target sentence, and the blue score is some sort of average or so over this score. So it's kind of involved metric, but let's say if you would make a perfect prediction for the translation, you would get a blue score of 100, but even for the human evaluation, during human evaluation, when the human translates the sentences, they won't get the 100 blue scores. They will get obviously much less, because you would need to guess exactly the correct answer. Also, the funny part is there are some languages in which, even though computer is generating not that good translations, people, they were optimizing a blue score, and they have a better blue score. A computer has a better blue score than the human translator, even though translations are worse. So then that actually raises the question of what's the proper metric to measure for translation, which is actually unclear. But you might think that blue score is just the surrogate loss or surrogate metric, and maybe you shouldn't, let's say, devote time optimizing something what should give you some indication of correctness, because if you will really optimize this metric, you might get the high score, but the quality, which is what you care about and what we cannot measure in easy way, will be actually worse. Actually, Ilya was so one of the big data sets in machine translation is one called WMP, and MP starts for machine translation. W, I'm not sure what it stands for. And it's actually funny that, as I mentioned, in the very similar time there were like two groups. So I was actually by that time at Google, and guys, they were about to publish their paper, and they discovered that folks from Montreal, they are working on the same thing. But also the cool part was that actually they were working even on the same data set, so the things were comparable. This is relatively large data set. It's like in terms of machine translation, it's like over 300 million sentences, words. You can say there is multiple languages out there. You can say there, if you want to criticize, you can say, oh, English and French, they are relatively similar, which is true. Translation between other languages might be actually more challenging. This is actually, it was trained on some part of data that was pre-selected in some weird way, but it doesn't matter. So one of the things is that as you train the models, you have to actually decide on the size of your vocabulary. So there is many words in English, and actually many things, it's unclear even how to process them. So let's say you might have a word like 1988, okay? And then the question is it a separate word or not? In some contexts, it might be actually a separate word. In some contexts, you would like maybe to copy it. But this actually gives rise to a huge number of words, and also you have proper nouns and stuff like that. It turns out that it's actually cheap to have a huge vocabulary in the input, but it's expensive to have a huge vocabulary in the output. The reason why it's expensive to have a huge vocabulary in the output is because you have to do softmax computation, and it's expensive. So that's why, for instance, in previous War 2 VEC, there was so much focus in order to make a model as fast as Thomas could, and he actually optimized the softmax itself. But of course, it gives a drop in performance. But his belief was to consume as much data as he could. So this model is actually quite massive model, and let's say run on multiple GPUs. It's like there is 4 layers of LSTM, and I would say as you look at the number of parameters, it's actually 400 millions of parameters. A lot of them, I think actually majority of them might be in the softmax and the word embedding, which is at the very bottom. But still, when you compare it even to the size of models in computer vision, so let's say AlexNet has the 60 million parameters, so it's way smaller. So this model is, I would say, relatively big, but I want also to warn you that not necessarily the bigger model, the better. So what happened recently in computer vision is some time ago, the best performance on ImageNet dataset, that's the, let's say, computer vision dataset, was achieved by Alex Kruszewski. The model had 60 million parameters. But over the years, or let's say 2 years later, people actually halved the error, so they achieved a much better model, but their model has 6 million parameters. So it's 10 times smaller, the sense, and has so much better performance. So I would say it's not necessarily a good thing just to throw a lot of weights out there. Okay. So as I mentioned, that works in the way that it consumes the words in one language, let's say English. When it consumes the words in one language, it doesn't produce anything, any output, and then as it comes to the translation, it starts emitting words in the different language. There are multiple layers. Each of the layers is 1,000 dimensional, so and LSTM actually it has both something called cell and hidden state. So single layer actually passes 2,000 activations in the single time step, and there are 4 of them. So here are some, let's say, hyperparameters that Ilya have chosen, but they are somewhat arbitrary in the sense. So you can, for instance, notice that even though this network is so massive, he doesn't have any like different initializations all over the place or something like that. It's like initialization is set uniformly between some values. Okay? But still, it took a time to build hyperparameters to get some, let's say, reasonable performance. So Ilya was able to actually heavily parallelize his model, and he's using 8 GPUs. So those are, I think, Titan X's. So he had 8 GPUs within a single machine, and he was able to achieve the performance of, let's say, almost 7,000 words per second. So his parallelization was done in the way that actually he assigned different layers, different GPUs, and as I mentioned, the final softmax is quite expensive, so actually he assigned multiple GPUs to softmax computation. So he assigned different GPUs to every layer, so I would say this actually means that in his case, hardware was in some way also dictating the architecture that he has. So let's say this way you couldn't have different number of layers or so. And he also wrote it in the log-free way. So as the information passes over here, it's actually independently passes between the GPUs. They synchronize as little as it can. Yeah. And you can think that, let's say right now, the representation for a single sentence, you can, for instance, concatenate the representation from every layer, and this way you have 8,000 dimensional representation for every sentence. So similarly as in the previous work, he was able to, let's say, run PCA on it and then see how it looks like. And this way you're actually getting representation for entire sentences. So the cool part over here is similarly as in case of word2vec that you have seen some analogy for the words. In that sense, you can see the similar structure here in terms of the representation for the sentences. So this is actually a classical example of sentence that actually changes the meaning when you switch order of words. So if you would have a representation that doesn't respect order of words, those sentences like Mary admires John and John admires Mary, they would be the same. They would be mapped to the same place. But in this case, actually, model respects the order, so it consumes the words from left to right. And you can see that actually representation that he's getting, it kind of respects the correspondence. So let's say we have here the sentence, John admires Mary. Here is a sentence, Mary admires John. And in kind of parallel place, you have a sentence, John is in love with Mary, Mary is in love with John. And similarly, John respects Mary, Mary respects John. Okay. Here is another example, and it's more involved, and I would say model also understands that some constructions in English, they can change the meaning in the sense, or there might be even passive voice or something like that. So here is a sentence, I was given a card by her in the garden, and here is another sentence. Is it the same meaning or is it different? It's even confusing for me. But the point is essentially that there is this parallel structure and so on. So the representation is able to some extent, the model is able to some extent to learn the representation that has some notion of meaning. This year the friend Ryan Kiros was training quite interesting model, very much based on the idea from previous work by Thomas Mikolov, so very similar to the Skiprogram. So a model is called skip thought vector, and he's saying, let's say as we have a sentences, let's consume an entire sentence with recurrent neural network, and let's try to predict entire sentences around. So let's say other sentences around. So let's say you can take few sentences around and try, based on the representation from a given sentence, try to predict sentences around. That's another instantiation of sort of an unsupervised learning. So you can imagine that we have infinite amount of data which is not annotated. So let's say the data that is used for translation is the annotated data. It's not as much as the data which is monolingual. You can get infinite amount of monolingual data. And Ryan suggested essentially just to consume sentences with LSTM or so and predict the sentences around. And that gave him a quite reasonable representation for sentences without, let's say, having a supervision as in case of Ilya's work with machine translation. So there was actually a few other tricks that Ilya had to use in order to be able to train the model for machine translation. So it turns out that one of the big changes that improved the convergence quite a lot, and it helped like the model really right away takes off, that gets the nice performance, like some reasonable performance even after training for the hour or two, was to actually reverse the input sentence. So why does it make sense and what is going on? So let me show you. So let's say we want to learn this translation, ABC, that is mapped to X, Y, Z, Q. One of the fundamental problems is that as the A corresponds to X, B corresponds to Y, C to Z, and let's say D to Q, that the distance between X and A is quite large. There is multiple time steps actually to pass this information, okay? So it's here on this picture is like a 4 time step. So the model cannot just like that learn the simple function. Let's say in order to even take off to know that there is a correspondence between X and Y, it has to propagate this information for many time steps. But in case if you revert the sequence, if the input sequence would be D, C, B, A, and the target sequence would be X, Y, Z, Q, then at the very beginning at least, the model can kind of learn that A would be very close to X. So it can learn this simple correspondence, and then afterwards, it's easier to learn the further on correspondence, like the Y corresponds to B, then the further on the Z corresponds to C. It's like it simplifies the task at the very beginning, and as you are getting somewhere, it's easier to progress further on. So that was one of the hacks that actually helped quite a bit. inverting input sequence. So then let's say initially, at least the distance between some of the words, it's much smaller. So you are hit much less by actually by the fact that you have to propagate the information through many time steps. Yeah, so actually that's what I just described on the previous picture. By reverting the sequence, all of a sudden, some of the words, they are becoming much closer in time, so it might be easier to learn the function. So this way, initially, at least the word, the sum of the words are very, very close toward the words that we want to, toward their target translation. So let's say A prime is very close to A. WMP is that's the competition, and as I mentioned, it's they care about something called blue score. Blue score of 100 means that the translation is exact. Here are some let's say some results. So what Ilya was able to achieve is not that it didn't by that time. It was not the state of the art. It didn't beat the state of the art. But wait a second. But the winner of WMT actually was, I don't know. There is still few blue points to get over there. So the winner of WMT was 37. Ilya was able to achieve something around 35 blue points. And I want to emphasize that actually it's really difficult to gain the blue points. And changing the blue points, usually even the small one, like of the half blue point and so on, it makes a difference in terms of the translation. And there are like papers in which the people, you know, they even they gain 0.2 blue point and they claim that it's significant. One of the things we wanted to analyze, or let's say Ilya wanted to analyze, what's actually when these models fail. So one of the things that you might think that might be an issue is length. The longer length, you might think, oh, it might be actually that might be something that will be problematic. But it turns out that even when you consider the performance depending on the length of the sentences, it doesn't make such a big difference. So let's say even if you had the test sentences of the length 70, the performance was sort of similar. So it turns out that actually what was the main issue is the performance on the rare words. So you can quantify, you can measure which words occur how frequently, and then you can take sentences just to, you can measure performance on the sentences which just contain the most frequent words versus the one that doesn't contain the frequent, that contains the infrequent words. One of the also problems in Ilya's system was the fact that as you limit the size of the output vocabulary because of the computational reasons, you replace all other words with an unknown token. So every time when you are actually predicting unknown token, it's clear that is a wrong answer, but it is what it is. So one of the, let's say, later on the proposals was to kind of fix the problem of rare words. That was by a friend of mine, Tank. And he was able actually to beat the performance of state-of-the-art in the machine translation. So he was able to achieve let's say, half the blue point above the state-of-the-art. Okay, I can even briefly say how he was able to achieve it. So his idea was to, for the very rare words, he was saying that that what the model should do is kind of copy them. So let's say if you have a pronoun, like, I don't know, Paris, or maybe someone's name, the proper thing to do is just to copy this from the input sequence to the output sequence. It should be that same word in the both places. So his model works in the way that for the rare words, he has somewhat placeholders, in the sense that you have 10 or 100 or so the placeholders that you, instead of putting unknown in the, let's say, target or the input sentence, you are putting a placeholder, you call it, for instance, X, and you put X in the input and X in the output. So that when the model predicts X, you are just copying the word from the input, and that was the trick, or more or less. I'm not sure if it was clear. So let's say some of the work that we have been doing later on, we kind of wondered in terms of how expressive are, let's say, the models that we train, and what are the limitations in the sense. So you can see that they can solve a lot of complicated tasks like a machine translation and so on. And the questions are, what are the limits? So if we would actually try to break it in the sense, let's try to solve as hard task as it is possible, when it will fail, okay? So from computational perspective, there are like tasks, like a kind of algorithmic task. You can ask, is it possible, for instance, to learn addition? Or maybe, is it possible to learn how to evaluate the program? So you can imagine that the same way as in the machine translation, you add the sentence in one language and then you try to actually produce the sentence in another language. The same question is it possible for neural network, you know, as the universal approximator and so on, is it possible to learn to evaluate the program? So that's actually in the most broad family of functions in the sense, okay? So obviously there is like several caveats over here. Like a neural network has a fixed computational time. So for instance, if inside of the program you would have a loop, obviously it's impossible to solve this problem properly. But nonetheless, we are wondering if we will constrain even the class of programs, what our models can learn. So we just generated the automatic data set, which was code in Python. So it's the correct code in Python that you can evaluate it. It was designed in the way that actually it can be executed by reading it from left to right. So this is an instance of, let's say, input, and here is a target. So always a target was just a sequence of numbers. So here you assign a value to a variable, you make some small operations on this variable, then inside there is some conditional statement, if statement, and you print an output. So that's the target. And you can perceive it the same way as in machine translation, that here is a sentence in English, here is a sentence in French, and you want to learn the mapping. You might also ask why it's even important. I mean, we know how to actually write compilers that would be able to solve this task with 100% accuracy. But you can think, oh, maybe it will give us some notion in terms of what these models can compute. So for instance, the question is how long the distance dependency they can carry, okay? Or for instance, can they memorize things, which might be required in this task because you might need to memorize actually values of variables. Another question is, can they do conditional computation? So if statement to some extent corresponds to the conditional computation. And you can also perceive it all as having many tasks within one. You can say, oh, here I have a task of addition, subtraction, and so on. So the way how we actually deliver data to this model is character by character. And similarly as in machine translation, we just need to emit symbols when it comes to prediction, not at the stage of actually consuming the input programs, but at the stage of actually predicting the output. It's not like in language modeling, but more like in machine translation. And our model is just a recurrent network, but I would say relatively small, 2 layers, 400 units, or actually it was the LSTM. Vocabulary size here is relatively small. Vocabulary size is of 42 because it's a character level model. So then every character corresponds to different input. So let's say there is, I don't know, there are digits, plus maybe there are possible characters, 26 of them, some special characters like, so there are digits, alphanumeric characters, maybe some special characters, so it adds up to 42 possibilities. And in output vocabulary, there are digits, and also there is the minus. Actually, I think here should be 12. And also one more sign is the end of sequence. So let's say model similar, the async translation, maybe I didn't mention it, but it can, it produces a character which is end of sequence character that you know that you should terminate. Yeah, and we train it until there is no improvement on validation. So as I mentioned, let's say even though the goal is grand, we train it on the very limited number of programs and so on, and it's not solving definitely it's not able completely to solve the problem of program evaluation, but it's able to do something. So it's trained on the operations like addition, subtraction, there is some multiplication, variable assignment, if statements, and for loops. But I want to say that actually for loops, they are kind of such a for loops that could be simplified to multiplication. So those are not the real for loops that require actually computation. And the way how we actually measure performance is, can say that the program is more complex if, for instance, there is more nesting. Or another way of actually quantifying the difficulty of programs over here is if the numbers that are used over there are of the larger scale. So let's say if I would have just the single digit numbers, it might be easier in compared to operating on 9-digit numbers. I want to also emphasize that actually the problem itself is not that trivial. So you can imagine that if you would be asked if you would, as the person, see even millions of examples of programs, and then you would be asked, please tell me what's the output, it wouldn't be that trivial to actually learn this mapping. So the way how actually computer sees it, it's more in the way as I presented on the display, because let's say the numbers or digits, they have no meaning whatsoever to computer. We know the meaning because we learned it over the time, but here it's presented in the scrambled way. So I took a number, or let's say characters from the input, and I randomly assigned a different character to it. And that's the way how, for instance, machine sees the input and our output. So that's the mapping that it's supposed to learn. So first of all, I want to show some qualitative results. This one is the instance of program where it actually is able to learn the exact prediction. But you can notice that many of these programs are actually, let's say, quite simple, even though there is some nesting in there, and the final output is actually just this 8794 plus 574. So it doesn't have to do much computation inside. It's also a question how to choose properly distribution of the programs, because you can choose the distribution of the programs in the way that you will make it harder. You can choose it in the way that you will make it simpler. In neither of these cases it will get 100%, but it's still surprising in the way that it's able to take off. So I will show you some numerical results in a second. So here it's actually model is able to properly predict the final output. Here it makes a single digit mistake. That's on the second value. And I would say, as we eyeballed, as we look on the results, it's often the case that the mistakes are in the middle. So it might be able to estimate what's the value of the leading number, or what's the number L, or what's the value of the digits. You can think that they're like a simplified algorithms. In some sense, you can estimate the magnitude of the things, and you can do computation modulo 10 or something like that. And as I mentioned, some of the examples might be, even though, let's say, theoretically there's supposed to be a lot of nesting, they might be actually very simple. So even though there is a lot of nesting, most of this code is actually dead, so the output is over here. And here is another example that it makes some mistakes. Actually, in case of this project, we're wondering if it makes any difference if we decide in the smarter way on the order of samples. So what I mean by that? You can imagine that when you teach a kid math, you don't choose exercises randomly from entire math. You are not giving first maybe a little bit of integrals, little bit of algebra, then some addition. It's rather that you order it based on some complexity. So first you start with simple concepts, and then when the kid is able to solve it properly, you move to harder and harder. So this concept was introduced some time ago. It's called curriculum learning, but I would say in the field of computer vision and NLP, actually, most of the time it doesn't make any difference. Or it even quite often hurts you in the sense. You can imagine that the reason why it might hurt you is because you are departing from the assumptions behind stochastic gradient descent. So stochastic gradient descent assumes that the samples that you are consuming, they are independent, but all of a sudden the samples that you are consuming are dependent. And you are changing distribution over the time. So you are training with non-stationary distribution, but the distribution that actually change over the time. And you can think also that all of a sudden you are asking network to optimize something that you don't care about. So let's say you care about the result on integration, but you're asking network to learn how to do addition. So those are some caveats here and there in the sense that, and also another kind of the typical problem with curriculum learning that the people experience quite often is the network. Let's say if we would conceptually, let's say we are about to first train the network to learn addition and then integration. A problem is that the network learns so well addition that it cannot, that after that, over the time, it cannot believe when it sees the integral character. It thinks, no, this is like, doesn't make any sense. I haven't seen this character ever. And it kind of overfits on the addition. It thinks that that's the entire life. The life is about addition. And it cannot, let's say, move on to another task. So let's say here we were playing around with several strategies for curriculum learning, and we were actually looking what are the improvements when you, what are the results when you change the strategies. There are some differences, but I wouldn't say that it's like huge. So, one of the strategies, we call it the baseline. It's essentially that there is no curriculum learning. So it means let's give to a kid the things randomly from entire curriculum of math, okay? Completely randomly. Then this one will refer to it as a baseline, okay? Then another one is called naive curriculum strategy. So it's in the way, let's train on addition until it gets above really some very high threshold, and then let's move to another task, and so on. Then the third strategy is called mixed strategy. So you can imagine that one of the problems with at least program distribution in the sense, or let's say when you sample the numbers, or when you sample nesting, or when you sample numbers, is that if you want to sample numbers from 1 to, let's say, 1 million, then actually majority of numbers that you will sample, they will have a large number of digits. You won't sample numbers that are small. If you have uniform distribution over the numbers from 1 to 1 million, you will maybe actually sample numbers that have 5 digits, okay? So one of the suggestions is maybe you should change the distribution over the numbers in that sense. So you might say instead of actually randomly choosing from 1 to 1 million, maybe we should first actually choose the order. So it's kind of the distribution over the logarithmic scale, and then within this order choose the number. Yeah, and then the combined strategy is essentially to make sure that we are doing curriculum learning, but also we are modifying distribution of the numbers, how we are showing it, and also one thing that we are doing, as far as I remember, is that you are not only training on the, let's say, just addition until you will reach some threshold, but you are slightly mixing up some other stuff. So majority of time you are doing addition, but from time to time you are surprising a kid and showing right now self-integration, and kid has no idea what is that, but at least it expects in future seeing the integral character or symbol, and it's not panicking. So let's say the performance is the following. So on one axis there is a nesting, on another one there is a length, and that's the accuracy of the prediction. So length is the length of the numbers from which we are sampling, and the nesting is, as we increase the nesting of programs, then it might be more difficult to actually predict the output. So if you have a very relatively small nesting and very short numbers, then accuracy of prediction of solving the task of consuming a program character by character and predicting the output, but this is actually, I want to emphasize, this is accuracy on the single character basis. And also one thing which we do here, which was a little bit criticized, is so-called teacher force. So as I mentioned before, in case of machine translation, when you want to output the final answer, you have to search over all possible, or let's say you have either to search over all possible sequences and then choose the one with the highest score, or you do beam search, okay? So that's the common way of actually obtaining the translation. So this problem, as I mentioned, is also a translation problem, but we're a little bit more sloppy in the sense. So there is another way of actually of getting some predictions, of getting translations, which is not completely applicable during test time. So you can imagine that if I want to translate a sentence, I can emit the first word, but then if it was incorrect, I can get from teacher what was the correct word, and then predict the next word, and then get the what was the correct word, then predict the next word, and then what was the correct word, okay? So it's somehow, it's the testing in the sense I should emit entire sequence and then compare it with the real one, but instead I'm just emitting one by one, and my teacher is telling me what was the correct answer. So this is kind of more optimistic. In that sense, as long as you have very high accuracy, then your own predictions might be used to feed it back instead of the teacher predictions. But when the performance is low, those things are not equivalent. So that's one of the caveats that I wanted to emphasize. So you can see that, let's say, as long as the nesting is relatively small and the length is relatively short, and the accuracy is actually surprisingly high for this variety of tasks, it was actually striking for me that, let's say, even I was surprised that it's possible to train LSTM on like a nine-digit numbers addition, and it achieves on the digit basis around 99% of accuracy. But still, it doesn't understand addition. So let's say if you look into longer sequences, it actually fails on correctly predicting them. But also, same thing, 99% of accuracy, this is also measured using teacher force. You can imagine that often the tasks, they might be solved in incorrect way. So for instance, if you want to do addition, you could memorize what's the result of addition of 3 digits, every 3 digits, or maybe every 2 digits. That's just 1,000 of combinations. You can memorize it all. And then when you have to add 9-digit numbers, you just add the two pieces separately, 2 by 2, 2 by 2, and you don't care about the carry. The problem is that, of course, if we'll increase the size of the network, we'll get the better performance on this task because the network will be able to memorize even more combinations for addition and so on. But still, the network is quite dumb in the sense that it doesn't understand the underlying algorithm which involves carry and so on, but only memorized quite a lot. So it's also another thing that I would like to warn you, that big data actually gives the illusion of intelligence. Systems, they are able to memorize quite a lot, and thanks to that they are able to solve problems, which is fine. But it's good to be aware of it, because often those solutions, they are actually far from the solutions which are intelligent and which would solve the problem completely. So here the funny thing is, of course, we can increase size of the network and all the performance will go up, okay? We can throw more data, all the performance will go up. But regardless of that, regardless of optimization technique, regardless of size of the network, these networks, they won't be able to solve this task properly. They won't be able to get to generalization 100% regardless of length and so on. So I just wanted to emphasize, to say also here that actually as we look at the different curriculum strategies, which was quite surprising, or let's say surprising in the light of the previous research where the improvements were rather negligible or not present. Here actually there is some improvement by using curriculum learning. So you can see that those are of the orders of, let's say, 10% absolute improvement from baseline to combined strategy. So that's the one that we advocate as the best one. So it was the combination of, let's say, naive strategy together with mixed strategy. And you can look into, let's say, comparison with all the strategies. So here these plots, they actually present the relative performance. So as we have a different curriculum, it shows what's the improvement in compared to the naive strategy. And in case of combined strategy, the improvement is always present. So as I mentioned, the thing which to some extent worries me is that there is some distinction between understanding and memorization, and actually we have to be careful about it if we really want to, let's say, build very intelligent systems. So obviously big data gives you a way to solve a lot of applicational problems, because you can, throw a huge model that will memorize all the things that really occurred, but it won't have a proper understanding of underlying principles, which is completely fine to solve the applicational problem. And I would say what is kind of ridiculous, it turns out that that's the way how we are able to solve majority of problems. We are able essentially to gather for any problem enough data and then train the massive supervised model to solve it. And we can see trends, for instance, in machine translation, that we are getting the performance gain is essentially coming from the size of training corpus. The bigger data set, the more performance we are getting. So it means that essentially the model is more memorized. Human might not need even that much, let's say, data to learn it. And one of the actually ways properly to test for the given skills is to design the tasks that the test distribution is very different than training distribution. So you can imagine the proper way of actually checking if a kid knows how to add numbers is to ask, please tell me what's the result of adding 99999 plus 1. And then the kid who really understands the underlying principle will be able to answer this question. But this example for addition is so much different from the training data of random numbers that model won't be able to solve it. Actually, I think I finished quite early. So here is some links to the code. So there is some of my LSTM code. There is also some code by Andrew Karpathy. he wrote a very nice blog post about the character level RNN. There is online generation demo by Ilya that you can type the, let's say, part of the sentence or the beginning, and then the model will generate the rest of the sentence for you. I mean, usually the people ask the models, what's the meaning of life? And then the models, they generate the answer. But also it's important, you might want to be actually careful with such a demos, because it happened to us a long time ago that we asked the model to generate stuff and then the model started cursing. And here are some references. I want to also say, I haven't said at the very beginning, but I can say it now, that the slides came from Thomas, Mark Aurelio, Rob, and this one, they came from Ilya. And I would say, actually, that's it for these slides. Thank you.
I think that now we have time for discussion.
Yeah, sure.
So if you have any questions, no problem. Ask.
So the answer is.
Okay, so I was just asking which framework did Ilya use to create this translation, machine translation network?
So the answer is following. Initially, actually, Ilya was playing with Torch, but Torch has some limitations in the sense, and I was quite impressed. I mean, Ilya is a good engineer. He wrote everything in C++. He wrote everything actually. Let's say he took from Alex some of his implementations that Alex is using in the framework called CUDA-ConvNet. That was the first release code for by Alex for convolutional neural networks. He also wrote there several routines for C++ for matrix operations on GPU. Ilya took it all and implemented his entire translation code from scratch. He was kind of annoyed that he cannot control things.
Especially if it has to work on 8 GPUs.
Yeah, that's the thing.
I have a maybe more generic question. When you are testing for accuracy of your algorithms, what kind of results do you consider good for binary classification and free category classification? And for test, as you said, when the training data is very different from the data you test on. What percentages do you consider good?
It depends on your baseline.
Let's say I don't have a baseline. I'm
So you
searching
have to
for a sentiment in a political comments that are very personal, and the sentiment is very subjective. And what kind of results could I consider good when I have, for example, 3 categories and no baseline?
So I would say that's essentially the problem of not having baseline. You cannot ever say if your results are good or bad. So you don't know as you have your model. Is it amazing or not really? So suggestion is take something the simplest possible you can think about, for instance, n-gram, and train, I don't know, SVM or logistic regression, and then you will see what's the result. And then you can, try to improve on it. Also, another thing is that you can manually do qualitative analysis. So you can look what were the predictions to see if they sort of make sense.
Okay.
Yeah. So those are essentially 2 things that you should do.
Okay.
Can I ask 2 questions? Okay.
Go for it.
I'm going to go for the more general one first. From your experience with it, would you say that you could learn algorithms with it? Because you had that last slide that I really liked, by the way, memorizing versus understanding. That's, I think.
So I would say it more memorizes, it doesn't understand.
Okay. That kind of answers my follow-up question, because my follow-up question would have been, could you take, for example, if you think of machine translation, I'm quite sure you can solve it with that, but let's imagine you have a sentence and then you use some algorithm from cryptology and then try to learn that, like infer the algorithm from that.
Yeah, I would say we had some crazy ideas like that, but they never pinned down. So there was this idea that a lot of cryptography actually relies on the randomness, but in reality, computers, they cannot generate completely random things. So let's say it happened that when the random numbers, they were not really random, that some like hackers, they were able to break some cryptographic ciphers, okay? So the question was, and it was the case that, for instance, second digit was more likely to be 0 than 1 with probability half plus 1 over 200 or something like that. And then the people had to improve or change the random generator. So we were wondering if, you know, as you have a sequence generated by a random generator, just looking at the, you know, the probability over the second or the first number or so, that's a very simplistic way of actually assessing the randomness. Maybe we would be able to find some minimal pattern over there, like get slightly above the entropy which would be given by the uniform distribution over the random numbers, and that would allow to solve some, you know, to break some cryptographic stuff. I mean, if you feel free to do it. We couldn't, let's say, maybe I spent like 2 days on it, but I think it might be possible, I don't know.
So I have a question about this gradient clipping. Do you clip the gradient on each coordinate, or do you scale the vector?
So, I mean, there is actually several approaches how to do gradient clipping, and I'm usually doing the simplest way. So, you have entire gradient, and I'm computing a norm for entire gradient, and then I'm and then that's the way how I'm computing the threshold, and then I'm rescaling everything according to it. So let's say then you can think that still within the, as you consider the stochastic gradient framework, then still the direction is exactly the same, but the magnitude might change. I mean, the things become more difficult and people depart from the assumptions when they do, for instance, gradient clipping in the distributed environment. So you can imagine, as you have the situation with 8 GPUs, that you don't want to synchronize GPUs in order to do gradient clipping. So then you are a little bit sloppy about it. It's still fine, it doesn't matter that much. Yeah.
Could you give me a bit of more intuition why LSTM prevents the vanishing gradient problem?
So let's have a look on the picture. So the simplest intuition, or the one that I strongly believe in, is that the way how RNN works, it takes the current hidden state and then multiplies it by some matrix. But in case of LSTM, it more works in the way that you have some state and you are just adding some new stuff to it. You are keeping it as it was. You might modulate it to kill it if you want, but rather you keep it in that sense. So there is similar unit called GRU. It's gated recurrent unit, actually developed by folks from Montreal. One of the reasons why actually they developed it is because LSTM turned out to be very slow in Tiano. Tiano is developed in Montreal because of some random reasons, so they developed their own unit, so it's fast in Tiano. But GRU works exactly in the way that the next hidden state is a kind of it's the interpolation between what what was the previous state and what the network predicted, and then it has the same behavior. we were also doing some time ago the analysis in terms of as you have, multiple gates here and there, which things matter. And it seems that the most important is essentially the forget gate in LSTM. But it's, as I mentioned, it's kind of, black magic. Yeah.
Who next?
Any other questions?
No question.
No questions.
Okay, we finished way earlier.
Thank you very much, Wojciech. We have to wait a bit for lunch because it is planned for 1 o'clock. And at 2 o'clock we have the next lecture, which will be made remotely by our speaker from Canada, Ruslan. So I invite you at 2 here in this room, and at 1 o'clock we will start our lunch in room number 3. Thank you very much.